Hey everybody, Dr. A here, and in this video we're going to be exploring an example of angle of twist. So let's go ahead and get started. In the given information, we're being asked to compute the angle of twist of the free end with respect to the fixed end of the shaft. And we're also being told that the shear modulus of the material the shaft is made of is 75 gigapascals. So the shaft that we're given has a fixed end at A and a free end at B, and at that free end we have an applied torque moment of 2 kilonewton meters. The entire length of the shaft is 0.8 meters, and the cross section is a hollow tube. So the hollow tube is sometimes called an annulus, and so what we have here is an outer diameter of 100 millimeters and then a wall thickness of 12 millimeters. Okay, so let's go ahead and get started. This is a pretty simple, straightforward example. We know that angle of twist is given by the formula TL over JG. Okay, now because this is a single segment shaft and the cross section is the same throughout the entire length, then we just have the simplified version of this formula. No summation here and no integral. Okay, we also know that the internal torque moment at any point inside of the shaft is just going to be 2 kilonewton meters. Now we can prove that if we draw a free body diagram of the shaft using method of sections. Okay, so at the free end of the shaft, we've got this 2 kilonewton meters, and then of course internally we know that the torque inside here, T, must equal 2 kilonewton meters going in the opposite direction. Okay, so if we were to put a viewpoint here and look into the cut, we would get T equals 2 kilonewton meters going clockwise. All right, now this is kind of unnecessary at this point because the 2 kilonewton meters is at the free end, and again at any point along the length of the shaft, the internal load, the internal torque is 2 kilonewton meters, again with a viewpoint looking into the cut going clockwise, but I figured I'd show my work there anyway. All right, so really the only bit of work we need to do here is get the polar moment of inertia, J, right? So it's a hollow tube or an annulus. So for a hollow tube, we're going to say pi over 32 times the outer diameter to the fourth minus the inner diameter to the fourth. Okay, now the outer diameter was given to us, that's 100 millimeters, so I'm going to rewrite that as 0.1 meters. That's the outer diameter. What about the inner diameter? Well, you were given a thickness here, right? So the inner diameter, which is the distance of the inside hole, is going to be the outer diameter minus 2 times the thickness. Why do we say 2 times the thickness? Well, you're taking that outer diameter here and you're multiplying the thickness on one side. You're subtracting, not multiplying. You're subtracting the thickness on one side and from the other side to get this inner diameter. So you get inner diameter. Let me clean this up a little bit. You get inner diameter is outer diameter minus 2 times the thickness. Okay, and so again, we can say 100 millimeters minus 2 times 12 millimeters, and we get 76 millimeters. So we'll get 0.076 meters just to use base units. Okay, now we can substitute our values in, and we're going to get phi equals 2 kilonewton meters multiplied by the length of the shaft, that was 0.8 meters. All right, and then we divide by JG. Okay, and so if we substitute J in there all together, we get pi over 32 multiplied by 0.1 meters to the fourth minus 0.076 meters to the fourth. And then G in that denominator is 75 gigapascals, right? So we need to have consistent units. Since we have 2 kilonewton meters showing up in the numerator, how about we express this as 75 million kilopascals. Okay, so if you're a little rusty on your unit conversions, you might want to review that. 75 gigapascals is the same thing as 75,000 megapascals, which is the same thing as 75 million kilopascals. All right, so we're going to punch this in our calculators very carefully. Okay, it's going to be very easy to mispunch something in your calculators here. So if I were you, I would try to type these in your calculators, type these values in your calculators pretty carefully. So I'm taking care of J right now separately and multiplying that by G. So I'm taking care of the denominator now. And then I've got 2 times 0.8 divided by that denominator. So I end up getting 0.00326 radians. Okay, now that's my answer. Now, what direction is this going? Well, this is going to be going clockwise. Okay, this is going to be clockwise. How do I know it's clockwise? Well, a couple ways you can recognize that this is the angle of twist clockwise. Number one, the applied load here is going clockwise if you were to put a viewpoint out here and look at it from this direction. And so obviously it's going to twist in a clockwise fashion. That's one way to think about it. The other way to think about it is from our free body diagram of our internal loading here, okay? So we put a viewpoint looking into the cut, all right? And by the right-hand rule, when we look into the cut, our fingers of our right hand will curl counterclockwise to be positive, but we end up getting a clockwise internal torque moment here, which by the right-hand rule would be a negative value, okay? But regardless, this would be result in a clockwise type of rotation based on either of these viewpoints. So that is our final answer. Again, pretty simple problem. If you found this example helpful to you, please hit like and subscribe and be on the lookout for other material like this. Thanks for watching.